Right, thank you very much, Dan, and thank you to all of you for being here. Again, apologies also from my side, of course. I think the projector next door works, we just don't have the credentials to actually access it. So that's why we're here today. Luckily, this one at least is working, and it's great to see a full house. I'm very excited to see many people who seemingly are excited about gravitational waves, which happens to be one of our main research areas here at the University of Birmingham. As we advertise here, we have an Institute for Gravitational Wave Astronomy, and some of my colleagues are also in the audience today. And I'm really happy to tell you about this kind of new kid on the block in terms of observations and astronomical things we can do with the universe to understand better how gravity works, what the universe is made of, and in particular look at exotic objects that many of you are surely familiar with, at least from science fiction, such as black holes and neutron stars. Now, to talk about gravitational waves, as the title tells you, we actually have to talk a little bit about gravity first to get everybody on the same page and make sure you all come with me on this really, really exciting journey. Now, this is something that is very familiar to all of you from your everyday experiences, right? Everybody has dropped something, clearly fallen to the ground, not flown up. That's the effect of gravity. And that sort of fundamental force description that we just have an attractive force between any two kind of masses or particles or energies has been around for hundreds of years, right? It goes back to Isaac Newton, who first published his empirical law. So this is really deduced just from observations and everyday experiences in 1687. And for the maths aficionados here, given you the formula, which just tells me I have a positive and attractive force between any two masses, like the Earth and the Moon. At least that's what Keynote tells me the Moon looks like. And it is proportional is 1 over the separation, so the distance between those two objects squared. So it's an inverse square law, and that's done the job for hundreds of years, and still is good enough for most, not all, of our everyday experiences. The other main concept that goes into that, apart from this being a universal law, it doesn't take any time for this interaction to propagate. It's instantaneous and everywhere the same. But what also goes into this concept is that time and space, so distances we measure, times we look at our clocks, they are absolute and they are distinct. They have nothing to do with each other. Time and space are two completely distinct entities. Now, all of this was kind of turned upside down in 1915, and actually a little bit earlier also, when Albert Einstein came along and introduced us to the concept of first special relativity, and then he generalized it to general relativity, or GR for short, because it's quite a mouthful. So if I say GR, I mean general relativity. That was in 1915, right? So this is like 250 years, 260 years after we have been living quite happily with our empirical understanding of gravity as just a regular force and one of the four fundamental forces. And it required us to really dramatically change how we think about this fundamental interaction. And of course, not everybody got on with that very well initially, and it took a while to actually establish that. So what are the key elements of general relativity, and what makes it in part a little bit hard to get to grips on initially? Well, first of all, already in special relativity, Einstein told us that time and space actually, they are entwined with each other. They're not absolute concepts, and they communicate, so to say, with each other. They're really entangled. And time and distance measurements don't mean the same for everybody. They can be different for different observers, so different people taking measurements, depending on their relative velocities to each other. Okay? So that concept remains also in general relativity. But what we now do is we factor in gravity. Because clearly gravity is there, right? We experience this every day. But in a very abstract way. It's no longer this attractive force between any two particles, but it is now what we call a geometric property of this four-dimensional space-time continuum, and that property specifically is called curvature. Now that sounds all very abstract. So let's look at a picture, so to say, a pictorial idea of how you can think about this. So here you can essentially see, for an instant of time, a slice of space-time, obviously in 2 dimensions here, not in 3 dimensions, right? So that's what you see here. And then you see different objects lying around in this space-time. Now, depending on how strong the gravitational field of each of these objects is, it will leave a different kind of dent in the fabric of space-time. Now, you might think, okay, the more massive, the more gravity it has, the bigger the dent is. That's a reasonable intuition, but it's actually compactness that really matters, which is the ratio between the mass and the size of your object. That's going to determine how strong the gravitational field is, and the stronger the field, the more curvature you get. Now, when you have this curved space-time now, and you send, for example, light from a star to us, we look at our telescope, we look at a star far, far away, then, of course, this light ray now propagates through that space-time. But if it goes close by some gravitating source, then you can see that the path is changed. If it goes far away from any gravitational source, it just goes straight through, follows its regular path, doesn't feel the effect of any gravity because it's nowhere nearby. But if I come close to a gravitational field, it's going to curve its path. And that is true for any object that you're looking at. I used the example of a light ray here, but that would also be true for any massive particle that you are moving in this space-time. So John Wheeler, very, very famous physicist, said that we can summarize general relativity in the following way, namely that space-time tells matter how to move, and matter tells space-time how to curve. And that's really what's illustrated in this nice graphic here by the European Space Agency. Now, that might still sound a little bit abstract, but now we have essentially the basis to talk about gravitational waves. But before we talk about gravitational waves, I have a little exercise for you. Show of hands. Who likes to use navigation systems to go from A to B? The majority of people. Excellent. Me too. I'm terrible at navigating, so I do like to type it into Google Maps and get a path. And I'm glad you did and came to our beautifully illuminated campus tonight to hear me talk about gravitational waves. Have you ever wondered how this works and what it has to do with general relativity? I can see some puzzled faces. Very good. So the basic idea behind this is a GPS system. So we have satellites that are orbiting at what is called a geostationary orbit, about 20,000 kilometers above the surface of the Earth. And we've got lots and lots of them orbiting around, and they have clocks on them. Very, very precise atomic clocks. And we have receivers on Earth, also atomic clocks. But we are now near the Earth. Earth clearly has a mass, so it curves space-time, right? There's gravity, as we experience every day when we drop something. Now, an effect of this entanglement of space and time, and the effect of curvature of space-time induced by gravity, is that time doesn't flow the same way for us on Earth as it does for the clock on the satellite in our GPS system. In fact, the clock on the Earth, which is closer to the gravitating mass, so deeper within the potential, it flows more slowly. So gravity slows down the ticking of our clocks. Now, when we start out with our two satellites, for this to work and actually give us a position, we need to synchronize them very, very well. So after one day, because of the effects of the gravitational field of the Earth, you have a desynchronization between the clocks in the satellite and on the Earth of about 17 milliseconds. Now, for comparison, if you blink with your eye, it takes you about 100 milliseconds to do that. So this is a really tiny, tiny, tiny discrepancy between the measurements on the satellite clock and on the Earth. But it has a huge impact. It's going to send you the wrong way by about 5 kilometers. So you aim to come here today, but maybe actually you're a Birmingham City fan, and you would have ended up at St Andrews Stadium, which roughly is about 5 kilometers straight line distance from campus here. So even though we might not think about it, general relativity and its quite abstract concepts indeed do have an impact on our everyday life to some degree, at least if we like to use the convenience of our sat-navs rather than old school paper maps. But let's go back to space, because I think that's why many of you are here today. So this kind of abstract theory of general relativity, of course, was received very skeptically by fellow scientists at the time. So if you want to convince your community that your radical change of how we have to think about one of the fundamental interactions, gravity, If you want to convince them, well, you need to make concrete predictions that you can go and test, right? You verify or you falsify. That's the standard principle, as Karl Popper told us, how we should be looking at our theories. Now, GR, of course, does that for you. And here's some very, very famous examples. So the first example here concerns the deflection of light. So we're again on Earth here, and we're taking our telescopes and we look out to very distant stars, and we just record the position of these stars on the night sky. Now, if there is no intervening mass, there are no gravitational fields interacting here, then as we've seen before, they should just follow, the quickest path in this unbent, so to say, space-time. But let's wait until the sun moves across our line of sight. So suddenly we have this massive body. Our stars at the very far distance are still there. So what happens to the light? The same as on the graph before, right? Suddenly, our light rays travel on this curved path. And so your perceived position will be different to where they actually are. Now, how do you practically measure this? If the sun is in the way, you can't see a thing, right? Other than the sun, very bright object. You wait for a solar eclipse to happen. And this is exactly what they did in 1919, the very, very famous Eddington eclipse, where they went to exactly do that. They monitored the position of stars. They waited for this eclipse to be in the line of sight. They went and measured the position of the stars during the eclipse, and they found exactly what was predicted by general relativity. Now, Newton's gravity predicts that too, but it's wrong by a factor of 2. So this is already, you have data, even in 1919, right, just 4 years after the theory was published. That was pretty hard to refute that, you're doing something crazy here. And in particular, you probably start to really think about, Newton might not be quite the right answer. Another interesting observation concerns the motion of the planets. If you combine Newton's universal law of gravity and Kepler's association with them moving on ellipses, you can almost very nicely describe the motion of the planets in the solar system. But already early on, people started to see some deviations from the prediction of the motion of the planet Mercury. And what happens, so Mercury moves also on an ellipse, like all the planets. In the focal point, we have the sun. But what we see is that the orientation of the ellipse over time changes. So you can see how it's like rotating around. So essentially this point here shifts over time as we monitor the motion of the planet. And again, the measurement matches the prediction from general relativity of this perihelion precession, as we call it, very, very well. So we have some quite strong data points in favor of this new, rather abstract theory of gravity. But it also made some more extreme predictions that actually didn't really take off in terms of convincing people until about the 60s and 70s. And 2 of those are black holes. So black holes, everybody in the room has heard what a black hole is. So in a very, very short form, it's just a small region of space-time which is so strongly curved that not even light can escape. So that's where the name black is coming from. No light escaping from it. You can't point your telescope and observe any photons from it directly. It's actually, mathematically speaking, a really simple object. It was one of the first exact solutions that people wrote down when Einstein's kind of maths theory came out in 1915. And it was a young chap called Karl Schwarzschild in 1916 who published this. And it's really simple. It's just a space-time region. There's no matter there. It's just described by curvature, and the physical properties are entirely determined by the mass, the angular momentum, so how fast it's rotating, if it is rotating, and it could potentially be charged. That's it. 3 very, very simple things that describe such an object. Now, of course, conceptually, this is much more complicated, right? So we have this kind of really strongly schematic here of very strong curvature in our space-time. And there's actually a sort of boundary point, so a boundary region, which is what we call the event horizon. And it's this region which disconnects the inside of our black hole from the outside here. And as we go further and further inside the event horizon, eventually we're going to hit a singularity, and what happens then, nobody knows. So this is where we really need to work hard to find a unified theory of quantum quantum dynamics, quantum mechanics, and gravity. But that's the basic idea, and it pops out of the equations, right? And I mean, surely in 1916 it was a sort of, okay, fine, it's a mathematical construct. What does it have to do with reality? Why do we care about it? And people were very, very skeptical. Eddington in particular was like, this is ludicrous. There must be some laws of nature that prevent something like this from happening. But as time went on, and we developed theories about stellar evolution, it became more and more apparent that we actually think that these types of really strongly curved areas of space-time, these black holes, form generically at the end of the life of massive stars. So what you see here is a sketch about the evolution of stars, really just a pictorial description of how stellar evolution kind of proceeds. So we're starting out with some cloud that fragments. So we have like small lumps that are collapsing under gravity and eventually form a protostar. Now, whether you go left or right depends on the initial mass of that star, and that will determine how it's going to evolve, and it will determine also what its final state is at the very end. So if we have regular stars like our sun, then they undergo regular evolution along what is called the main sequence. So they just burn the elements in the core, they form new elements, so they produce radiation pressure. Outwards, eventually they're going to turn into a red giant and then get rid of the outer layers in a beautiful planetary nebula. I'm sure you have seen beautiful Hubble images of that. And what's remaining at the very end is a white dwarf, which is a relatively small star compared to our sun. So for some numbers, solar radius is about 700,000 kilometers. Now, the white dwarf that will eventually appear at the end of the life of our sun will only be a few thousand kilometers, right? So this is a really small star, but it's going to be quite bright. So that's why we call it a white dwarf. If you started out with a more massive star, kind of the initial phase is the same, but then eventually you form what is called a super red giant, and that is going to go supernova. So it's going to end up in a massive explosion, at different types of explosion. They can trigger different types of supernovae. But the key point is, at the end, what comes out of these are two things. It's either a neutron star or it's a black hole. So these are your three options, depending on how massive your initial star was. So by the 70s, this was the standard picture. So they are no longer just some sort of math solution that pops out of some crazy equations, right? But they started to become, astrophysically at least, reality. Now for them, of course, to be reality, we have to talk about actually measuring them and observing them, right? Are these objects really, really out there? And so people have been observing black holes indirectly by looking at how the gravitational field of a black hole interacts with its surrounding environment. That could be light, but that could also be the dynamics, how it influences the motion of other objects around it. So you see a couple of examples here. Let's start with this one, with these two here. These are artists' depictions and illustrations of a black hole that is close by a regular star, another star. And if that is close enough, of course, the gravitational pull of the black hole starts to strip off matter of your star, and it can form an accretion disk, maybe a jet-like structure, stuff that radiates across the electromagnetic spectrum so we can observe it with regular telescopes. And then we can infer, okay, I can't see anything in the middle here, so I conclude, if it's consistent with the predicted observation, that there's a black hole of a specific mass sitting in there. We could also have a star that flies by and gets destroyed. It gets what we call tidally disrupted, causing then a stream of matter that's going around. Again, this will give you light. It will give you a flash of light in a particular spectrum that you can go and observe and then conclude, well, this is consistent with what I would see if there was a black hole of a particular mass sitting there. And then these two images, I guess, most of you will have seen in the last couple of years popping up. The black holes, the supermassive black holes here in the centers of M87 and then Sagittarius A star, of course, our own center of the Milky Way galaxy. And what you see here is, again, actually the traces we get from radio observation here in particular. So again, matter and how it's interacting and emitting radio waves in the vicinity of these central dark regions of our galaxy. And we conclude again that there are very, very heavy black holes now sitting millions to billions of solar masses, depending on the system you're looking at. Or we look at the dynamics. So here we have a view of over 20 years or 30 years of data where we're tracing the motions of stars towards the center of our galaxy, which is marked by the little star here. And so in particular, look at this yellow one. They were able, I think, over 25 years to trace out a complete orbit of that star. And from that complete orbit, you can again infer what sort of gravitating object that I don't see do I need to have sitting here in the middle in order to explain the motion of those stars in the center of the galaxy. So this is the result here from Andrea Getz's group, who won the Nobel Prize a couple of years ago. So black holes do seem to be some form of astrophysical reality out there. Now, finally, what about gravitational waves? They are also one of those predictions in general relativity, and they do not exist in Newtonian gravity. So this is really something where you can't find a Newtonian analog, but you really have to go general relativity. And what are they? They are vibrations. We had this four-dimensional space-time. That is not static. We can bend it, right? By putting masses in, we can curve it around, which means it has some sort of elasticity if you want to think about it in that sort of way, which means we can send vibrations through that space-time. And GR tells us these vibrations are waves, transverse waves, and they have to travel at the speed of light. And in principle, roughly speaking, you can say any form of accelerating mass is going to generate these gravitational waves. And that includes black holes, of course. So this opens a completely new opportunity for us to actually directly look at information or at waves that are created by black holes themselves. So we don't have to look at how they interact with their surrounding, but really something that's coming from the dynamics of the black holes themselves. And how do you do that? Because I said we need accelerating masses, right? So if we just have a black hole sitting there, it's not accelerating. It's not going to give me any gravitational waves. But if you have two black holes coming together, and it's almost Valentine's Day, right? Then they can form a binary system. We remember space-time tells matter how to move and matter tells space-time how to curve. So we have local curvature here that is going to drive accelerating motion in this binary system here, causing these ripples of space-times traveling outwards from the source at the speed of light. And this is the golden ticket, essentially. So this is what we can try to measure. Now, binaries will be the main focus for the rest of this talk, but there are other gravitational wave sources, cosmological gravitational wave sources, astrophysical sources out there in the universe. And just like electromagnetic radiation, right, they span a huge range of frequencies, of wavelengths, of periods, whichever description you would like to think about them, stretching to being very, very short, from seconds to milliseconds in terms of their duration or their frequency. This is where we are looking today, predominantly with our observatories that we have. But we can go to lower and lower frequencies, and that means looking at different sources. For example, at the mergers of galaxies. So if we have two of these supermassive black holes come together in the galaxies, if that happens, they will also create gravitational waves. But we can also look at the very, very early universe. So here you see a picture of the cosmic microwave background, but the expectation is that we might get something similar from gravitational waves from various processes in the early universe, even before the time of the CMB. So another opportunity to actually look at a regime that we can't access with electromagnetic radiation, maybe bringing us closer to the Big Bang and the beginnings of the universe. Now, binary systems are routinely observed in electromagnetic radiation, not when they have black holes, obviously, but when you take two of these neutron stars. So your other end-of-life opportunity for a massive star, so to say. And there's a very famous binary system, which is the Hulse-Taylor pulsar that was discovered in the 70s. And it consists of a neutron star and another neutron star, but we call it a pulsar because it has a strong magnetic field. And so it allows us to emit radio pulses at a regular pace. So we can monitor these pulses, right? As they spiral around each other, we can monitor these pulses and measure them. Now, as you've seen from the graphics before, what happened to our waves, to our binary? You probably noticed that they were coming closer and closer together, and eventually these two black holes smashed into each other. That's the fate for any binary that is emitting gravitational waves, because gravitational waves carry away energy and momentum from the source, and that leads the orbits to decay and eventually form a single object at the very end. Now, this is also true for our Hulse-Taylor binary pulsar. But from that, we do not directly observe the gravitational waves, but we measure these radio pulses. And our colleagues have measured these over 30 years. So they're monitoring this pulsar for many, many decades. And what they measure is essentially very, very similar to what we saw in the perihelion advance. We're measuring essentially how the orbit decays. Or you can think about it how the period, so how long it takes the binary to go around each other, changes over time. Now, the dots here are the data points that are measured over 30 years. And the black line is the prediction from general relativity if you just assume the emission of gravitational waves and nothing else. And it matches absolutely beautifully. Now, why have we not seen these waves so far? So the period of the Hulse-Taylor pulsar is about 7 hours and 45 minutes. And the gravitational wave frequency is 0.07 millihertz. So it's very, very, very low frequency. And that's a regime, if you remember the graphic from before, that we're not quite observing at the moment. So at the moment, we're looking for gravitational waves between a few hertz and a few kilohertz with our current generation of observatories. But in the future, there will be a much wider window in frequency ranges open to us. So we call this the indirect detection of gravitational waves. Now, can we do something about directly measuring them? Well, yeah, we can. So let's think about what's the effect of such a ripple of space-time going through some region of space-time. Now, what it does when the wave travels through our patch of space-time, it actually stretches and squeezes space-time in directions that are orthogonal to each other and perpendicular to the direction of travel. Now, this is really nice if we think about that, because how can we utilize this? It effectively means that we're changing distances, right? So, if we measure distances between freely falling objects, like illustrated here, and we're sending our gravitational wave into the screen here, then it's going to periodically stretch and squeeze, which means it's going to change the distance periodically between any two of my particles on that ring here. That's great. We're very good at measuring distances, right? We have devices to do that. And that's exactly what we're going to do. But how large is this effect? And I'll tell you, these graphics were massively exaggerated. The average size of a human hair is about 0.1 millimeters. Now let's make that an atom, right? You take your human hair and you divide the radius or the diameter by 1,000,000. That's what's going to give you the size of your atom. If you want to go and look at the nucleus, you're going to divide it by another 100,000. So you end up with really, really, really small things, but we can measure them quite well, right? We have excellent technology to measure these. So how large is the effect of a gravitational wave in terms of stretching and squeezing? It's on average 1,000 times smaller than the size of a proton. So that's a 0 with many, many zeros before you see a 1. So how on earth are you going to measure that? Such a tiny, tiny, tiny length change that is induced by gravitational wave, even a gravitational wave that is created by something as extreme as two black holes clashing into each other in space. Well, you have to build a very precise instrument. And we have those. We use interferometry, laser interferometry, in order to measure these really, really small relative length changes that are induced by a passing gravitational wave. So how does an interferometer work? we have a laser beam that comes in, gets split, and then we have two arms that are perpendicular to each other, because remember, the stretching and squeezing was in perpendicular directions. So we're sending our laser light in. Do pay attention to the troughs and the peaks. So the wavefront of your laser light gets reflected then at some endpoint in each arm. They come back, they recombine, and then we measure them at some photodiode output at the end. Now, what do we observe on our output screen, right? You remember maybe destructive and constructive interference of light, right? If they line up, we get a signal. If they don't line up, they cancel each other out, and we get a dark port signal. And that's what you see kind of illustrated here. So what happens if we now send a gravitational wave from the top through our interferometer? Okay. Dramatic. I don't know what happened. You should have seen the stretching and squeezing quite clearly. Let's play it again. So we're sending our wave through, and right, it stretches and squeezes our arms, but in orthogonal directions. So that means when you have the wave that is perfectly coherent initially, when it gets reflected, we are producing this interference pattern, this very characteristic interference pattern, as we're changing the length in these interferometers, but not equally, right? So at one moment in time, the light's going to travel more this direction, and a shorter length this direction, and vice versa, right? And that's going to give us this characteristic pattern that we deduce. And our interferometers are very precise, and they can really pick out these tiny, tiny length changes that are induced by a passing gravitational wave. All right, so today we have a network of gravitational wave observatories based on this interferometric principle operating across the globe. We have the two LIGO detectors in the United States, which are 4 kilometers in arm length. We have the Virgo detector in Italy, 3 kilometers. We have a small facility of 600 meters in Germany. And then we have the Kagra Observatory here in Japan, 3 kilometers. And in the near future, we're also going to have another observatory in India. So that's what the landscape of gravitational wave observatories looks like at the moment. And this is what LIGO looks on the inside, in case you're wondering about it. So here you can see the outside picture I took last year in Livingston, one of the detectors. You can see the beam tube. So this is where our laser light's going to travel down from the central station all the way up to the end, 4 kilometers that way in Louisiana. Here you can see these endpoints where our laser light gets reflected. So these are mirrors, highly polished mirrors. Only 1 in about 3 million photons gets absorbed. That's how good their quality is. Here you can see actually one of the central stations here, where also the beam splitter optics is contained. And if you're wondering about the vacuum, it's one of the finest vacuums that has ever been created by humankind. So we have 1 trillionth of an atmosphere in these beam tubes. And you can also see some of our nice colleagues here working on the input optics as well as the electronics here. So now that we know what a gravitational wave is, how the detection works, what they're actually going to do, and what we're looking for, without any further ado, I give you GW150914, the very first direct detection of gravitational waves that later this year in September will celebrate its first, it's 10 years of detection, so to say. So I hope your ears are ready for that. All right, so that's it. That is the first detection of gravitational waves. You can see 2 data streams here because we have 2 observatories operating. So we had LIGO Livingston down here and LIGO Hanford up there. And what you're actually looking at is what is called a time frequency spectrogram. So you are seeing here in color this funny arching sort of evolution in time. And we notice that the frequency goes up, and I hope everybody picked that out as well from the sound, which has just been slightly upsampled so you can actually hear it. But the frequency range, you can see here is between about 20 and 260 hertz. That's the first gravitational wave detection we had. So how do we know this is a gravitational wave? I could tell you anything, right? Show you a pretty picture and say, oh, there's two black holes clashing into each other, right? Why should you believe me? Now, the reason you should believe me is general relativity. We can very, very accurately predict what the signal, the gravitational wave signal of two colliding black holes looks like. It's complicated, but we can solve the equations, and we can tell exactly, depending on the masses, on the spins, on the location, on the orientation of the source, what the expected gravitational wave signal is going to look like. And it has this characteristic chirping evolution, as we call it. That's why the New Yorker found it appropriate to have birds on its front cover here, where we have our two black holes going around each other. We said they're losing energy, they're coming closer together. That's reflected in the frequency of the wave increasing until the two clash together, and then they form a final black hole that is initially perturbed, but then you can see here it stops, right? It goes quiet. Because we're back to just having a lonely black hole sitting there. No more gravitational waves. That's it. It's gone silent. Maybe it finds another partner in the future, but that is it for now. And you can really think of these waves as being the DNA or fingerprint. They are unique for every single binary you look at. And we can determine by comparing the theory to the observation what the properties are. And here you can see an example for 150914. You can see the actual data here from the two observatories. Now you can really see the gravitational wave as a function of time here. And overlaid here, you can see the best fitting predictions from general relativity. Now you notice it is not exact, of course, because our data are not perfect. We have noise sources like you have in any instrument that you have, but we can statistically assess the significance and the agreement between the prediction and the data. And there is no reason to think that anything else is necessary to explain the waves that we have seen. So what do they tell us? They tell us that what we observed are two black holes, one 36 times the mass of the sun and the other one 29 times the mass of the sun, that clashed into each other. Within a stretch of only 0.2 seconds, they radiated away gravitational radiation that had the energy of 3 suns. So you take 3 suns, 3 times our sun, and you convert it into gravitational energy. That's what was contained in just 0.2 seconds. That's hugely energetic. In fact, gravitational waves are some of the most energetic events that are actually taking place in the universe. It is created when our universe was about 1 billion years younger than it is today. Because remember, gravitational waves travel at the speed of light. It's not instantaneous. We have to wait for them to actually reach us and come to us. And so I think this was very, very exciting. But things have moved on since then, right? That's 10 years ago. So what have we been doing for the past 10 years is what you might ask. So this is an image here that has no gravitational wave information on it. It's just a graphical representation of mass distributions of potential black holes that we indirectly inferred from observations of light. So these are the pink dots here. And the yellow dots down at the bottom here are actually neutron stars, like pulsars and neutron stars themselves. Again, just observed in the electromagnetic radiation spectrum. And the axis here is solar masses. So, no gravitational waves, just black holes from EM observations and neutron stars. You notice hopefully a couple of things here. First of all, there seems to be quite the boundary here at about 20 solar masses. So no electromagnetically inferred black holes suggest that there's anything that is heavier than 20 solar masses, unless you go to the very extreme and we go back to our supermassive black holes like observed with the Event Horizon Telescope. But what about everything in between? Do they not exist? If not, why not? And the neutron stars here you can see, they are quite light, between a solar mass, maybe some even lighter than a solar mass, and at most about 2-ish. Now you also notice there seems to be a gap between the black hole masses and the neutron star masses. So interesting observations. So how have things changed since gravitational waves came along? So this is data. I can't show you the most up-to-date data because they're not public yet. But this is the data after the third observing run. And in blue, we've now filled in all the LIGO, Virgo, Cagra black holes. And in orange, we've filled in what we think are potentially neutron stars observed in gravitational waves. Now, I hope you noticed two things instantly. We are probing much higher masses suddenly. These black holes here, beyond those 20 solar masses that we had in the EM, they do exist, definitely. They're definitely out there. What's also interesting is there are clearly objects now, more objects than before, that are in this lower mass gap here. So maybe that gap isn't actually a gap. There's no good theory that tells us why there should be a gap, but we hadn't observed much in there. And that makes you question, right? But clearly we are starting to populate this now. The other thing that's quite interesting is the shaded box up here between about 50 and 150 solar masses. Stellar evolution theory that I told you before actually tells us that we can't form black holes that have masses between 50 and 150 solar masses as just the end product of the life of a massive star. So where do these black holes come from? Could they be second generation? Could they be mergers of black holes? Interesting questions. And as you can see right now, we are quite limited in the range up to about 200 solar masses. Future experiments will allow us to probe even higher black hole masses. Some personal highlights was the definitive observation, I would say, of the first intermediate mass black hole. So the remnant that was created in this collision here was about 150 solar masses. Again, there was observational suggestions before, but they all went away over the years. But you can perfectly explain this observation with an intermediate mass black hole. I showed you in this lower gap, I don't know if you noticed it, but there were some that had a blue half and an orange half. Because we can't really tell, are they very light black holes or are they quite massive neutron stars? We don't know. 1908-14 is an example here of such a case. With these many blue dots that you have seen on the previous page, we are now really starting to probe the mass spectrum of black holes, which is clearly much more extended than what we had thought before. So we can essentially map out the mass function or the distribution of black holes per mass spin, and currently it's looking like we have an excess of black holes at about 30 of a weight of a mass of about 35 solar masses, and a sharp decline as soon as we reach about 80 solar masses. We also seem to have quite a lot of black holes actually around 8 solar masses sitting here. So what are the physical processes? Why is that? Where are they coming from? Many interesting open questions. We can do cosmology with gravitational wave observation. Some of you might have heard of the Hubble tension between our standard electromagnetic means of determining the expansion rate of the universe, which is encapsulated in the Hubble parameter, and gravitational waves provide us with a new way, an independent way of constraining the Hubble parameter. Right now, you can see we are a bit like Switzerland, very neutral, can't really break the tension. But in the future, hopefully, we'll get the precision to actually make an independent measurement of the Hubble parameter. And then we'll find out, is there maybe some interesting physics going on between the late time and the early time universe. And last but not least, for those people interested in more fundamental physics, we can constrain the mass of the graviton with gravitational wave observations. GR tells us they travel at the speed of light. If you do not believe in general relativity, but maybe a massive theory of gravity, you'll be interested in what is the mass of the graviton. Now you can use gravitational wave observations to put the strictest bound from any observations of graviton mass on the graviton mass itself. And as I said before, we are now starting to fill this supposed lower mass gap. So maybe there isn't really a gap between 3 and 5 solar masses. Maybe we just haven't seen them before. Maybe they just don't like pairing up with low mass X-ray binaries, for example. Who knows? But we are clearly starting to see that now. And I can see Dan is standing, but I want to tell you one last thing about another kind of wave, because so far it's all been about black holes. But, as you've seen before, we have also been observing from neutron stars. And I want to tell you a little bit about the neutron stars because they're quite spectacular, because we can also start to learn about nuclear matter and the properties of matter, which is something we can't do with black holes because they're just curvature. They're very cool. But if you want to learn about fundamental properties of matter and how matter behaves under extreme circumstances, they're not your best bet to look at it. So here you can see the observation of GW 170817. Again, you can see the time frequency range. And you see, again, hopefully everybody's noticing the chirp here. But I spy with my little eye a much longer duration here. Same frequency range, we're starting at 20 Hertz, but now we're observing like half a minute of gravitational wave signal. And that already tells us that we're looking at objects that are much, much lighter. Now, we didn't just observe the gravitational wave, but it was truly spectacular, this event, from an entire multi-messenger perspective. Gravitational waves? And NASA's Fermi satellite detected a coincident high-energy gamma-ray burst. And this gamma-ray burst was subsequently followed by a huge, what we call kilonova explosion. So it was really the real, the full deal, the real deal, everything. You have the gravitational wave, you have the high-energy gamma rays, and then you have electromagnetic radiation across the entire rest of the electromagnetic spectrum. And what was particularly spectacular about this, it was hypothesized that these gamma ray bursts, which are quite regularly detected, and some of you might have been Dr. Gombert's talk some time ago, and people said, yeah, some of these short gamma ray bursts, we think they are created by the collisions of neutron stars or a collision with a neutron star with a small black hole, but there was no proof. It's hypothesis. Now we have the coincident. So we can very confidently say that at least a class of these gamma ray bursts is created by the collisions of two neutron stars. And the same goes for these kilonovae. These were hypothesized. There were some candidates that went away over time, but now we have it all. And we found out that actually the vast majority of precious elements is created in these kilonova explosions, in the collisions of these neutron stars and the aftermath. So anybody wearing any gold or silver or platinum in particular, you're wearing cosmic bling, so to say. But from a pure fundamental physics perspective, neutron stars are particularly exciting because they are some of the most extreme cosmic laboratories that you can think about when you want to learn about fundamental interactions on the very, very, very small scales. Now, we have a relatively poor understanding of neutron stars. We think they are formed in this way of an atmosphere, and then we have a crust structure, and then we have an inner core at some point. But what really is going on in this inner core, we don't know. Because the densities and the pressures are so extreme that they're multiple times the nuclear saturation density, so we don't actually know how matter behaves. And it's very, very difficult to probe this on laboratories on Earth. Because if you look at the kind of poor man's QCD phase diagram here, neutron stars sit at the very high density region and low temperature. Now, if you smash things together at the LHC, because you want to try to create a quark gluon plasma or something like that, you had very, very high temperatures. So they are in a completely different part of your phase diagram. And so you may not necessarily be measuring the same thing. So these are really exciting laboratories where we can learn about what's really going on with matter under these extreme circumstances. Are quarks going to be deconfined? Are there some phase transitions going on? We don't know. So they are very, very exciting. And now you probably ask, okay, so how can you learn about this from neutron stars? It's all in the wave. So what you see here in the background is black hole gravitational wave, same as the one before, but it's overlaid now with a binary neutron star waveform. And I hope you can see it in the blues and coming out so well. But what happens here is that even though they initially might look the same and line up perfectly, you see they're starting to run out of phase. The neutron stars are going to merge earlier than the black holes. And then crazy stuff happens afterwards, because depending on the masses and the rotations of the neutron stars and what is called the equation of state, so that tells us how matter potentially is behaving in those stars, you can get different outcomes. But it is this slight dephasing here that really allows us to learn about nuclear physics, because we can map this constraint from this dephasing onto what is called a mass radius curve. So that connects the mass of a neutron star with the radius, or more fundamentally, we're looking at the equation of state connecting the pressure with the density of the neutron star. Here you can see our measurement from GW 170817. And then you can see some theoretical equations of state. And what you see is some of them are definitely excluded by our measurement alone. Many of them are consistent. Which one is the right one? We don't know, but it's one of the big science goals for the future of gravitational wave observation to make precision measurements of the equation of state of neutron star and learn about the behavior of matter under really extreme conditions. And so I'll close out with saying that right now as we speak, we are observing. LIGO and Virgo are both online. They are monitoring the gravitational wave sky, and we will be observing until the beginning of October. We started in May 2023, and so far we have 190 confident detections. Now, the blue stuff you saw on the plot after the third observing one was about 90. So we're adding another 190 to those. So it's really, really growing, and we're really starting to uncover the demographics and the populations of neutron stars and black holes in the universe. And you never know what's out there, right? Maybe there are new classes, new sources. Maybe we find some violations of general relativity. Who knows? If you want to have a look yourself, we have the Gravitational Wave Open Science Center, where you can also download the data. And you're more than welcome. There's a bunch of tutorials there as well. I see some students, so if you want to play around with gravitational wave data yourself, you're more than welcome to do so. And then in the very near future, we will undergo some slight upgrades. Our detectors will improve a little bit more, some technology improvements, and then we will start observing again towards the end of 2027, hopefully running until the early 2030s before we're then getting ready for the next generation. And I'm going to stop here, but I do have slides on the next generation. So if you're interested, just use the question time to ask me about that. And thank you very much for your attention.